Hello students, as you know we were talking about electric potential. In my last lecture we had taken out the derivation on potential due to a point charge. Of course we had learned the formula for electric potential. The very first formula was V equal to W upon Q naught. From the same formula we had taken out for potential difference. Then the relation between electric field and electric potential, E equal to minus dV upon dr. Then potential due to a point charge. These were the formulae which we had discussed in my last lecture. And of course, for a group of charges, if you want to take out the potential, then that can be written in the form of summation Qi upon Ri, I equal to 1 to n. These were the formulae. Or for a continuous charge distribution, you can write integration of dq upon r for continuous charge distribution. So these were the formulae, and now today we are going to carry on further, and the topic shall be potential due to an electric dipole in the end-on position and the broadside on position. So let us see, students. Potential due to an electric dipole. Case 1, end-on position. This is the dipole. The method is just similar to the one where he had taken out the field intensity due to an electric dipole. You know, this is L and this is also L, and there is a point P. You can draw straight also like this. This is the point P and this is at a distance r from the center of the dipole. So you have to find the electric potential at the point P. So first of all, potential at P due to plus Q charge. So that you can write V1 equal to 1 by 4 pi epsilon naught Q upon R. So Q upon, what is this distance? R minus L. And potential due to minus Q charge, that is V2 equal to, I told you potential is a scalar quantity, so for a negative charge the potential is negative. From minus Q, what is the distance? R plus L. So this is R plus L. Hence net potential at P is V equal to V1 plus V2. This is the net potential, or V equal to, add both these, you can take Q upon 4 pi epsilon naught common directly, you can take common. So this is 1 upon R minus L plus minus of this, so minus 1 upon R plus L. Okay, so this is R square minus L square is the LCM, so R plus L minus R minus L means plus L, cancel out R and R, So q upon 4 pi epsilon naught into 2l upon r square minus l square. This is the formula. I'll rub this portion. So you'll get V equal to final form. What is Q into 2L? That is dipole moment P. So 1 upon 4 pi epsilon naught P upon R square minus L square. This is the form. If you will write now, if R is too much greater than L, then neglect L. Therefore, V equal to 1 by 4 pi epsilon naught P upon R square. This is the formula for electric potential due to an electric dipole in the end-on position. So I hope students you have understood this. And now we come to case second. Case 2 is broadside on position. Means the equatorial line of the dipole. So this is the dipole and this is the line which is passing through the center and perpendicular to it, and on this line we take a point P which is at a distance r from this. So this is minus q and this is plus q, this is L and this is L. You make this triangle, you mark this AB like this. So once again, because potential is a scalar quantity, so net potential will be the algebraic sum of the individual potential. Means you find the potential due to this charge, find the potential due to this charge, add both the potentials, you will get the resultant potential. So what should I write now? Potential at P due to minus q charge. This is V1 equal to 1 by 4 pi epsilon naught minus q upon, take this distance as AP, no? And potential at P due to plus q charge. So you take V2 equal to 1 by 4 pi epsilon naught q plus q upon BP. So therefore V resultant, this is the symbol for broadside on position, V1 plus V2. So this will be, you take q by 4 pi epsilon naught common. So this is minus 1 upon AP plus 1 upon BP. But by symmetry, you see the figure, this side is equal to this side, AP is equal to BP. By symmetry, therefore V means the resultant potential in the broadside on position is 0. This is the formula now. This is the value. So I hope you have understood. This is quite easy. So these were the two cases for potential due to an electric dipole. And now we come to the next topic, and that is equipotential surfaces. Equipotential surfaces. What are equipotential surfaces? As the name indicates, the surface where the potential at every point is the same, that is known as equipotential surfaces. So a surface, you can say like a conductor, no, like a sphere. On every point, at every point on the sphere, the potential remains the same. Or in space also, you can take any surface where the potential is same throughout. So you need to know the properties of equipotential surfaces. Like first one, you can say, suppose this is an equipotential surface. Okay, this is an area of an equipotential surface. So this is one point A and this is another point B. So no work is done in taking a charge Q from one point to another on the equipotential surface, because the potential is same at every point, so there is no change in potential. That means dV is equal to 0, no change in potential. So what is work done? W equal to QV or QdV? No. So dV is equal to 0, therefore dW equal to 0. So no work is required if you displace a charge from one point to another on the equipotential surface. This is, you can say, one property. Then you can say no two equipotential surfaces can ever intersect, because if they do so, then at the point of intersection they will give two directions of the same electric field, which is impossible. This is the second property of equipotential surfaces. Then one more important property comes out for equipotential surfaces. If I say, since you know E equal to minus dV upon dr, this is the formula. For same dV, if I say, then dr is inversely proportional to E. This is one important property. So wherever the spacing of the equipotential surface is less, that means the field is strong field, and if the spacing is more, that means weak field. Means the spacing between two equipotential surfaces is inversely proportional to the electric field intensity. It means the field is stronger where the spacing is less. So these are the properties of equipotential surfaces. One more property you can recall, that electric field intensity is always perpendicular to all points on the equipotential surface. This is one more property. So these are certain properties of equipotential surfaces. So I hope you have understood these points of equipotential surfaces, students. And now we can talk about one more topic, that is work done. Work done in rotation of a dipole. Work done in rotation of a dipole in an electric field. So this is the field. No? So if I say this is the dipole, and you turn the dipole like this by some angle theta, so we need to do some work. So in this field, suppose this is the dipole, the stable position of the dipole, and if you need to turn the dipole by some angle, suppose for small angle d theta, dw will be equal to how much? Small amount of work done in moving the dipole by a small angle d theta. dw will be tau into d theta. Already you know what is tau? Pe sin theta d theta. Okay. So therefore, for rotation by an angle theta, total work done, this is integration of Pe sin theta d theta. Okay. So this is how much? Pe, and this is integration of sin theta d theta. So if I say take the limit 0 to theta, so this is Pe. What is the integration of sin theta? That is minus cos theta, 0 to theta. So this is Pe minus cos theta minus cos 0 means plus cos 0, or you can say W equal to Pe into 1 minus cos theta. This is the formula for work done in rotation of a dipole in an electric field. So, students, I hope you have followed these small topics of today. We need to go for some numericals also in this chapter. In my last lecture, we shall finish the remaining one or two topics of this chapter, and of course, I will take the numericals. So, practice. We'll meet once again. Goodbye.